around between yes, okay, between 15 and 20 minutes, okay. And then there will be a round of questions by each of us.
Okay.
And then we will ask all of you for a while to get out of the of the Zoom, or we have to Skype ourselves. So we need to talk, the three of us, to decide the marks. Okay. So well, you can start.
Okay. So first thing, do you hear me well?
Yes.
And can you see my screen?
Yeah.
Okay. So I will start. Okay. So good afternoon, everyone. I am Raul Lopez Martin, and I'm going to present my master's thesis, Functional Networks of Weather Events Propagation Between Airports. So meteorology and climatology are two very relevant fields, not only from a purely scientific point of view, but also as they play a very important role in day-to-day life. In some areas, this role is critical, such as in aviation industry, where extreme weather phenomena can lead to flights getting cancelled or delayed, airports being closed, and also safety of the users put at risk. For example, during high-speed crosswinds during landing can jeopardize the safety of it. So these reasons, despite being few, clearly show why to get a deeper understanding on the processes and phenomena underlying meteorology and climatology and the variables associated to them is very important. One of the most novel approaches to do so is the one known as functional networks, and I'm going to explain in a very simple way how it works. The first thing, it uses large sets of time series of the desired variables under the desired circumstances. Then statistical methods are used to find relations between these time series. And finally, complex networks are used to represent this result, in which nodes are the time series and an edge exists between two time series when a relation is found. Here we can find a graphical representation of a functional network of this work down here. And in this case, nodes represent time series associated to a given spatial location, and an edge, here represented in blue, exists when a relation is found between two time series at different spatial locations. So in this project, what we are going to use is the same methodology, this functional networks methodology, to find relation between time series at different spatial locations for each of the following variables: temperature, difference between temperature and dew point, that has a lot to do with humidity, and wind speed. The two main goals that we expect to obtain from this project are the following. First, being able to find, or at least make hypotheses about the physical phenomena that govern these relations that we will find, and also to evaluate the functional networks framework under some novel characteristics or circumstances, or at least some circumstances that have not been widely evaluated in the past literature. So, the first thing that we needed, according to the past scheme I have just shown, is our large sets of time series. Hence, we need a data source. And in this case, the one that we are going to use are METARs, which is an acronym for Meteorological Aerodrome Reports, which are normalized weather reports issued at every airport, giving the current meteorological information at that location. They come in a text string-like format in which you have two identifiers, one for the airport and one for the day at time and time at which it is issued. And then we find the rest of the information about the meteorological variables encoded here. What we are going to do with them is we're going to generate one data set per each airport under analysis and ordered in chronological order. And we are going to use from them the wind speed, temperature, and dew point. To get a little bit deeper on METARs, there are some benefits on fusing them as a data source. The first one is that they have a very high temporal precision, as they are issued either every 60 minutes or 30 minutes. For the case of all the airports that we are going to use, they are issued every 30 minutes. Then the variables have also a very high precision, as safety of the aviation industry highly relies on having the correct values for them. Also, there are a large number of variables that appear in the METARs, as there are a lot of different variables that are relevant for aviation industry. And finally, their availability is easy and up-to-date, as there are different public websites that as soon as a METAR is issued, it's uploaded there. And well, maybe most important in my case, my supervisor has this data set, or this data, sorry, for the largest 249 European airports since 2019 up to 2022. He allowed me to use them, meaning that I started this project with this step already fulfilled. Then, of course, there are also some drawbacks, but because we are going to try to face them throughout this project and either solve the problem or minimize the negative effect that it may have on the result, we should better call them challenges, and are the following. The first one, as we have just seen, an extraction process is required to obtain the data from the methods. Also, as they are issued at airports, they have limited spatial locations, and these are heterogeneously distributed. And finally, there is a non-zero probability of losing data, mainly due to the long-winding retrieval process. Additionally, very important for this project, to the best of our knowledge, this data source has never been used before in this framework, meaning that we will be able to assess how this framework works under a data source of the characteristic of methods. So now one may think that we already have our time series as we have our data sets, but the reality is that we have to perform some steps before having them. The first one is a filtering phase in which we have to eliminate any method that comes with either an invalid date or an invalid value for any of the variables that we want to analyze. Then, now in principle, we would have our clean time series, but now, due to the statistical tool that we are going to use to find relations, which in our case is going to be the Granger causality, for analytical performance, it requires for the time series to be complete. So we have to generate the missing values that we have lost due to the filtering process. And we are going to do so using interpolation. But first, we have to check if the time series are suitable for interpolation, because we want then to first have a large enough amount of real data after interpolation, so we do not end up analyzing artificial data. And also, we want the quality of the interpolation to be good enough. So after running some tests, only 154 out of the 249 airports had a valid data set for temperature, dew point, and wind speed. So from now on, we are only going to work with those 154 airports. Then, sorry. Now it's moment to perform the interpolation for the valid time series. And here I want you to focus in these last two columns, which are two metrics or two values that evaluate magnitudes that evaluate the quality of interpolation, mean absolute error and root mean square error. And they show that the interpolations are quite good because these values are close to or below the lower bound for the precision of these three variables in the methods. Finally, we will already have our time series clean and complete, but we have to run yet another extra step, again, due to the Granger causality that we are going to use, and is to normalize the time series to make them stationary, because this methodology requires the time series to be stationary to function correctly. So what we are going to do is we are going to substitute each of the values of the time series by this value here, which is basically a score-like methodology in which this mean here is calculated with the values for the same variable and the same location for the 15 posterior days and 15 prior days at the same time and of the same minute and hour than the value that we are substituting. And this standard deviation is calculated with the values used to calculate the mean. So after doing so, this substitution, we check that the resulting time series are stationary. Indeed, they are. We use two statistical tests. And just to make it clear, at this point, we are already using the time series of difference between temperature and dew point. We have subtracted the interpolated time series of dew point from the interpolated one of temperature, and we have normalized this one. So we end up with normalized time series for temperature, difference between temperature and dew point, and wind speed. Now, as we have already our time series prepared to use it with the statistical tool, it's time to introduce it. Granger causality is the one that we are going to use. And let's, to explain it, let's assume that we have two time series, X and Y. And what we want to know is if additionally using past values of Y, I'm able to better predict values of X than only using past values of X. So what I want to check is if this regression model here that uses the two sets of values is able to better predict values of X than this one that only uses the set of values of X. If the former outperforms the latter, we are going to say that in a Granger causality sense, Y causes X with a given lag, M lag, which is a tunable parameter, that is the maximum past step that we are using in our predictions. For the case of this project, for the time series that we are going to use, we are going to ask for this result to be statistically significant. So we are going to check it through a wall test, and we are only going to accept the causality between two time series if the p-value is lower than this threshold value here that accounts for a Conferoni correction. So we now have our statistical tool, our time series, and we are going to generate 3 sets of time series, each one of them containing the time series associated to each one of the variables under analysis, and we are going to run the Granger causality methodology in each of those sets between each pair of time series in both directions, and for a set of lags ranging between 30 minutes and 24 hours in intervals of 30 minutes. And in case for 2 lags the causality is statistically significant, we are going to stay only with the one that is more statistically significant. So overall, we end up with 3 networks, one for each variable, in which the nodes represent the spatial locations of the time series, here represented in blue, and an edge exists between 2 time series, of course, when a relation is found. Here are represented in black, and here they do not account neither for directionality nor for whether 2 edges exist or only one exists. But of course, as this network is directed, we are going to take this into consideration while analyzing the result. So moving forward to the results, the first thing that we are going to analyze is the information transmission metrics of these networks. We are going to focus on it because this causality can be, in this context, can be understood as a propagation of the tendency of the variables. So it's interesting for us to see how they perform in this propagation process. And when comparing it with Erdős ranging networks that we are going to use as null models, and looking at the set scores, which are here given between parentheses, we see that they are much worse in information transmission than their random counterparts. That is telling us that these variables, this tendency propagation process, they do not perform it on an optimal way, or this less likely to this process to occur than on this random network. Also, this is telling us the difference in the result, that definitely the result that we are obtaining from the networks that we have just constructed are completely different from random. The latter can be also seen by checking some spatial distribution of metrics. For example, here the in degree, this is for the difference between a temperature and dew point network, but from now on, every single result that I comment stands for all the 3 variables, despite only presenting one. And going back to what I was saying, clearly this distribution of in degree is non-random. These last 2 results can be seen as a validity test for the Granger causality. And looking to this result, we see that the nodes in the central part of Europe, they take the largest value of the in degree, and the farther away we move, or a node moves from this region, the lower its value is. This also accounts for the out degree, despite not being seen here. So we could say that it is something that happens for connectivity. And from a qualitative point of view, it can be seen that on average, the closer a node is to the rest of them, the larger its connectivity is. This qualitative idea can be verified with a quantitative one if we plot the probability of an edge existing as a function of the distance between the two nodes it connects, in which we see that the closer the 2 nodes are, the more likely is for a connection to exist. So we see that there is a clear dependency of this probability of an edge existing with the distance. So what we are going to do now is that we are going to build a new null model that inherits this probability of an edge existence distribution. So in this way, what we are going to be able is first to assess the role of distance, or how much does a factor distance plays in the networks, and also to have a null model that is able to reproduce the spatial properties of the network, so we can see under that spatial layer of the networks how random the networks are, which was something that with the Erdős ranging networks used as null model we were unable to see. So let's keep in mind this null model that we have just introduced, and let's move to another step, which is a network subdivision that we are going to perform, originating with a distinction that Granger in his original paper made, which was differentiating between causality, that was when causality between 2 time series existed only in one direction, and feedback when the 2 possible causalities existed. This also makes sense to take it into account, this difference in this project, because it's not the same for a tendency to propagate in one direction than to propagate in both directions. So using the same idea, we are going to subdivide each of the networks into one accounting only for the causality-like relations, causality subnetworks, another one accounting only for the feedback-like relations, feedback subnetworks. So we are going to now analyze each of these subnetworks for each of the three variables using first the null model we have just introduced, the Erdős-Renyi networks also as a null model, and also the metrics of the complex networks that we also use to analyze the total networks. And by doing so, we are able to make some hypotheses about the process underlying the relations in each of these subnetworks. For the causality subnetwork case, our hypothesis is that this tendency propagation is generated by westerlies. Westerlies are wind data streams that, when evaluated over long time scales, they blow from west to east. They occur in the Forel cell, which has a latitude range that contains the area under analysis, which is mostly the European continent. So, if this hypothesis is correct, what we would expect is to see the majority of the edges pointing eastwards, because if there is a phenomena that can be transported, that is generating a given tendency at a given spatial location, if the wind blows from west to east, we expect that this causality relation points towards the east, that the phenomena is transported towards the east. Also, we expect the distance property to be unable to reproduce and explain most of the metrics, because we are now saying that whether a relation exists depends on the relative position, not on the distance between them. The first point can be clearly seen if we plot the distribution of the edge direction in quadrants, in which for the causality subnetworks, in which we see that the eastward direction is clearly predominant. And also, this is not satisfied by only considering the distance factor, because this null model that only contains the distance factor is unable to reproduce this result. Also, we can see that distance cannot explain other properties such as connectivity, because here we see that if we plot the out degree for each airport as a function to the mean distance to other airports, there is no tendency whatsoever given by the distance. So these 2 points allow us to validate the previous hypothesis. And moving now to the feedback subnetworks, our hypothesis is that the propagation of the tendencies that these subnetworks represent are due to the mutual influences between locations due to how close they are. To validate this hypothesis, we should see in the results the following characteristics. First, that there is a clear influence of distance in the results and characteristics, and more specifically, that there is an inverse proportionality relation between distance and connectivity, because now we are saying that a relation, the probability of a relation taking place, depends only on how close they are, because the closer they are, the most likely is for a tendency to propagate from one point to the other and from the other to the one in both directions. And also we are expecting the edges to have no privileged direction, because again, now we're saying that whether a relation exists or not depends on the distance, not on the relative position. The first point, we clearly see it by plotting, for example, the probability of an edge existing as a function of the distance between the two nodes it connects, or the degree of each airport as a function of the mean distance to other airports, that we clearly see that they show inverse proportionality relations with distance. And here we're working with degree because the feedback subnetworks can be represented as undirected networks. And moving to the second point, now going back to working with feedback subnetworks as directed ones, we see no privileged edge direction whatsoever, as almost a quarter of the edges fall on each quadrant, and the same thing stands for the null model that only inherits the distance property from the feedback subnet. So, all in all, from this result, we have been able to first find physical significance of the result, or at least make hypotheses that have been validated using the results. And also it's worth commenting that this hypothesis that we have proposed, the processes of them, they match the time scales in which we are working, which is 3 years, because they can be seen as climate patterns. Additionally, the conclusion that we have seen on the results allows us to conclude the following. First, that the functional networks methodology is resilient under data sources as METARs, which are data sources with low spatial resolution and inhomogeneity of data. This was something that is not usually seen in past literature because they usually use very high spatial resolution data sets. Also, we have been able to see that metrics from complex networks are suitable to unveil information. This is something that has been also used in previous literature, but never under a data source of this kind, of the mentioned kind. And also that non-random results were retrieved by Granger causality methodology, as we saw in the comparison with the Erdős-Renyi networks as null model, which is something that is telling us that granular causality is a correct methodology to use in this framework. This was something that, again, has been used in past literature, but we have also checked in this case in which we have used low spatial resolution dataset. So overall, what we have been able to see is that this framework, meaning the use of low spatial resolution datasets combined with granular causality to find relations and complex network metrics to obtain the results, is suitable to use in meteorology and climatology. And finally, an article presenting this analysis and the subsequent results is under preparation. And that was all. Thank you very much for your attention.
Okay, so thanks, Raul. So then we will start with the round of questions. So maybe I can start with Sandro. That is the one that is farther from the work. Okay.
Shall I stop the recording, right?
Yes. I think that is good.